How's it going? Hope you all are doing alright today. Are there any questions before we get started? Doing alright. Just got a little bit more to go and we'll be through this. You may have noticed I did not get your test graded yet, but I'm anticipating getting that done this afternoon. I had put it off till yesterday, and then last night I just didn't feel like doing anything, so here I am. 21, 23, and 25 on homework, okay? Okay, so 21, we have log of x plus log of x plus 15 equals 2. Now, 9 and 19 also. Alright. So, with 21, we have two logarithms on the same side here, so step 1 is to combine these logarithms together. Because they're added, we know that we can multiply what's inside. So we have x times x plus 15. And so let's rewrite this. X squared plus 15x. And this is log with no base listed, so it's log 10. Now that's important because we need to know what the base is, because our very next step, since we have log equal to a constant, is to convert this into exponential form, which makes it 10 to the second equals x squared plus 15x. Alright, so 10 to the second is 100. And because we have a quadratic equation, we'll take that 100 and subtract it over so that we can get it equal to 0. And then we can factor, solve, and then check our answers. And so we think about what multiplies to, what multiplies to negative 100 and adds to positive 15. So that is 20 times negative 5. There you go. So we know that's x plus 20 times x minus 5. So we can find two potential solutions. X equals negative 20, x equals positive 5, and if we plug those in, we know if we plug in negative 20 here, we just have log of negative 20. Well, we can't take log of a negative number, so that just simply does not work. 5, however, plug in log of 5. That's a positive number, so we can take the log of it. 5 plus 15 is 20. That's a positive number, so we can take the log of it. So 5 is valid and our only correct answer. Okay. All right. Mm-hmm. 23 log of 7x plus 6 is equal to 1 plus log, this is x minus 1. Now in this case, the logs are on opposite sides. One thing we did not talk about is that just like any other term, we can move logs from one side to the other. Let's take our log of x minus 1 and subtract that over to the left. Those cancel. Now these are being subtracted, so we know that we can combine those. We'll make that log of 7x plus 6 divided by x minus 1. Now that they're on the same side together, we can combine them, and because they're subtracted, we combine them by dividing what's inside, as so. We just have a 1 left on the right hand side. Now, again, we have log equals to a number, so we'll have to convert this to an exponential. But notice, again, this is log base 10. So log, log by itself, is log base 10. 10 is implied, but it's important for us to know that it's there, because that's what allows us to convert this and actually get a number we can work with. So we convert that, and it becomes 10 to the first power equals 7x plus 6 over x minus 1. Okay. 10 to the first is just 10. Now, what we would do in this case, there's two ways to think of it, but they both amount to the same concept. We can either multiply by the common denominator, or we can simply cross multiply. But effectively, they do the same thing. If we cross multiply, we do 10 times x minus 1 equals 1 times 7x plus 6. So that's 10x minus 10 equals 7x plus 6. Either way, we arrive at this equation, and now we can solve for x just by moving terms around. You add the 10 over. So 10x is equal to 7x plus 16. Subtract 7x from both sides. So 3x is equal to 16, and then divide by 3, and that gives us x equals 16 over 3. And this one actually checks out. 16 over 3 is it's a little bit bigger than 5, so if we plug in 5, 7 times 5 is 35, plus 6 is 41. That's going to be a positive number. And then 5 minus 1 is 4, so that's positive also, so it checks. So the big difference there in 23 is that we do have to move the log from one side to the other. That way we can set up a situation where we can combine two logarithms and have it equal a constant on the other side, and then convert and solve from there. Alright, 25. We have log base 2 of x plus 7 plus log base 2 of x plus 8 equals 1. This is actually a lot similar to 21. The reason I put two of these on there is that there is definitely one of these on the exam that you'll have to do. Final exam. So we combine these once again. Because they're added, we'll have to multiply the two binomials. Now we have log base 2 over product equals 1. The next step is to convert, since we have log equals to a number, convert it to exponential form, so that'll be 2 to the first equals x plus 7 times x plus 8. Now 2 to the first is just 2, and we go ahead and FOIL this out. It's x squared plus 15x plus 56. Now, next we subtract the 2 over. That way we can get it equal to 0, because if it's quadratic, we want it equal to 0, generally speaking. So that leaves us with 0 equals x squared plus 15x plus 54. So now we need two numbers that multiply to 54 and add to 15. And that is it's 9 and 6, I believe. Yes. So that'll be, and they're both positive because both of these are positive. So it's x plus 9 and x plus 6. Now that gives us two answers. X equals negative 9, x equals negative 6. Now if we plug in negative 9 and attempt to check, negative 9 plus 7 is negative 2, and log of a negative 2 will not exist, so we know negative 9 is not valid. Negative 6, however, if we plug that in, negative 6 plus 7 is a positive 1. That's a valid logarithm that we can take. Negative 6 plus 8 is a positive 2. That's also valid, so that is a valid answer. And so we do end up with just x equals negative 6. Okay. All right. Amanda, you also asked for 9 and 19. Let's see. Now 9 is easier than it appears to be. Log base, that's a 4 of x plus 4 equals log base 4 of 15. Now, whenever we have a logarithm equal to a logarithm, like we do here, we can essentially, since both logs are equal, then what is inside must be equal as well. Now essentially we can get rid of the logarithm and just say x plus 4 is equal to 15. It's only when we have this exact situation where we have just one single logarithm on both sides of the equation. That's the only time we can just get rid of them like that. Otherwise we have to do a conversion like we've seen in the last three problems. Now here, once we get rid of the logarithms, we just have x plus 4 equals 15. We only need to subtract 4 and we have our answer. X equals 11. And if we plug in 11 plus 4 is positive 15, that one checks out. So it's a valid answer. The key time that we tend to have answers that may be invalid is something like 25, where we have to combine two logarithms together by adding or multiplying, as it turns out to be, and then solving it from there. Now 19 is quite a bit more involved. I'm going to go to a new page of paper for that. Okay, 2 times, this is the 6, 2 times log base 6 of x minus 5. And honestly, that happens a lot with logarithms. We just have to be careful. Plus log base 6 of 9 equals 2. Now, we did one similar to this, except the one, I think the example we did, they were subtracted rather than added, but the spirit of the example is the same. Whenever we have this coefficient here, we know we have these two logarithms. Our goal is to combine them together, but we have this coefficient here. We would want to first deal with that. Now, what we mean by that, by dealing with it, is we need to get it inside the logarithm instead of on the outside. And so we have a property that says 2 can be moved up and made the exponent inside. So we can make this log base 6 of x minus 5 squared plus log base 6 of 9 equals 2. Now, because we end up with the two logarithms added together, we can combine them by multiplying what is inside. So there'll be x minus 5 squared times 9. That equals 2 now. And similar to 21 and 25, because and 23 actually, all three of them, we now want to convert to exponential form, which would be 6 to the second equals all this. Now, 6 to the second is 36, so we can go ahead and do that. And now, this is a great time to just go ahead and divide by this extra 9 that we have on the right. So it leaves us a 4 on the left-hand side equals x minus 5 squared. Now, similar to the problems, sorry, Brock, I'll get to your question in a second. Similar to the problems that we worked back in chapter 1, whenever we have a square equal to a number, we can just take the square root of both sides, and we'll end up with plus or minus on the right, square root of both sides, so we end up with plus or minus square root of 4 is 2 equals x minus 5. So we can say either 2 equals x minus 5, or we can say negative 2 equals x minus 5. Add 5 to both sides. That means x is equal to 7. Add 5 to both sides. That means x equals 3. So we have two possible answers here, 7 and 3. Now 7, if we take away 5, is positive 2, and log of a positive 2 is valid. So 7 checks out. So if we plug in x equals 3, 3 minus 5 is negative 2. Log of a negative 2, regardless of base, is invalid, so that is not correct. So we just end up with x equals 7 as our only valid answer. Now, Brock, you asked, how do we determine if two similar logs, whether to cancel, subtract or divide, or add or multiply? Well, let's look back at the examples we've done. Whenever we just have a single logarithm on both sides, like we do here, we can just cancel a logarithm. That's the only time we can cancel a logarithm and just solve what's inside. You know, all the other problems that we worked here are more along the lines of these two problems, where we have two logs added together equal to a number on the right. And so when they're added together, we can combine them by multiplying. That's our I think we called it our addition rule or multiplication rule. It depends on how you look at it, I guess. But once we combine those, then we can convert to exponential form. We have to convert that because we have log equals a constant. So there's really two scenarios: either log equals log and we cancel the logs, or log equals a constant and we convert to exponential form. And that's really the only two routes that we have there. So it just depends which one comes up as. So if we have log equals to a constant, as happens most of the time, we convert to exponential form and solve the equation from that point. We did have another example, 23, where they ended up being subtracted. We'll save review questions to Wednesday. I do have a little bit more from 6 and 7 that I'd like to get through today. On 23, when we subtracted over this logarithm, we were then able to combine these by dividing what was inside rather than multiplying. And that's the difference between addition and subtraction, is if they're added, we multiply the insides together, and if they're subtracted, then we divide the insides together. Hopefully that addresses your question. It may well be. It may well be. There's a little bit more today that we just haven't looked at yet this semester. Yes, there can be a negative sign outside of a logarithm. Usually when that happens, that means there's two logarithms being subtracted. not just a negative logarithm by itself. I guess it could work either way. Yeah, I guess it wouldn't be that big of an issue. What we would usually do in that case if there's a negative logarithm is shift the negative to the other side and deal with it later. Oh, I gotcha. So if we had something like this, for instance, let's say log of x squared equals negative log of 9. We do that. What we would have to do first is take this negative coefficient, because this is a negative 1 here, and we would have to rewrite that as log of 9 to the negative 1. Basically, when we have a negative log, it's like there's a negative 1 multiplying it, and the negative 1 would bring inside as an exponent with our third manipulation property from section 6.5 that we looked at last Wednesday. You know what, August? I am not sure. I will talk to the two people that have been organizing that and get back to you on Wednesday. Okay. And it may just be that I have to upload the exam as a quiz in Canvas, and you take it through that with the lockdown browser. Now, I think that's probably what it is, but you have to sign up for a specific time, but the quiz will be there the entire time. I'll figure out the specifics. 10 a.m. is a good time. That's like when I'm most awake. 8 a.m. is not when I'm most awake, it turns out. But, I've taught college algebra enough that I can keep up with it. Alright, we need to continue on this. Alright, so continuing section 6.6. August, you're taking it day 1, wow. Hopefully it goes well. Might as well tear that band-aid right off and just do it. Plus it'll be fresher. There's the reasoning there. Now, we still need to look at solving exponential equations. We looked at logarithms already. And we have two primary methods that we can apply here. One, if b to the x equals b to the y, then x equals y, and that's what we had applied earlier in section 6.3. The other is that if b to the x equals y, then we can take the log of both sides bring the x down as a coefficient and then divide by log b to solve for x. Let's look at how we can apply this one. We already looked at this one in section 6.3, but this one's kind of new territory for us. Let's say we have 3 to the x is equal to 12. Now, if this is a multiple choice question, I can guarantee you one of the answers is going to be 4. But remember, we're not multiplying 3 times x. It's 3 raised to the x power. And 3 to the 4th is different than 3 times the 4. So, the way you deal with this, since our first thought is, can we write 12 as a power of 3? And that's where we would apply this first approach, is if we can write the 12 as a power of 3, then we have base 3 on both sides, cancel out the common bases, solve what's left over. That's just not the case. We can't write 12 as power of 3. So instead, we can take log of both sides. Now, the other approach that we could use here is that we convert it from log to exponent, from exponent to logarithm, and that actually works. This is the generally preferred method, though, just taking the log of both sides, because that's what we tend to do in the applied mathematics, like physics and engineering, other applied mathematics. That's the general approach that we like to take. It could be log or natural log, just one that we can solve in our calculator. Now, again, the x here is now that we're inside of a logarithm, the x is an exponent, and we can apply our third manipulation property to move that x out to the front. So it's x times log 3 equals log 12. And we can say x is then equal to log 12 divided by log 3. Calculator, just a non-graphing calculator, just like, yeah, scientific for sure because we need the log functions, but non-graphing because there is graphing on the test and they're not going to let you use a scientific or graphing calculator. So if you're doing in-person testing, they might have some scientific calculators you can borrow if you don't have one that's non-graphing, but otherwise you should just have a basic scientific calculator. Yeah. Alright, so we have log 12 divided by log 3. And that comes out to be 2.2 26. And so that'll be our answer then. That's the power that 3 must be raised to in order to equal 12. Now, given enough time, you could probably go through, say, okay, 3 squared, that's 9. 84 plus is not okay. That's a big graphing calculator. We can't use graphing calculators. Something in the 30s would be much more appropriate for TI calculators. TI 30, 36, both of those are adequate. If you keep trying hard enough, you could figure this out. It'd take a while, but you can finally get it to where it's a 12. Anyway, I'm not suggesting you try that. It's much better just to go through the process. But there are trial and error methods to this. Yeah, it works regardless, August. I did it all in one step. So what's going to happen is if you approximate them individually and then divide, then that means our answer won't necessarily be as accurate. So your answer may be slightly off, but 84 not okay. It's a big graphing calculator. You can't have a graphing calculator. So Amanda, anything in the TI 30 series? 30s, 36, those are good scientific calculators that are not graphing. That's strange. Is it a Windows computer calculator? Because those are notoriously odd at times. And that could be it. It's probably only a minor error anyway, so if it's like multiple choice, then you would immediately be able to pick out which is the correct answer, because it should be very close to the one that you came up with. If it's fill in the blank, then I would grade accordingly, which is it will be fine in my eyes. Know that those are just for storing values to memory or manipulating memory values, Brock, so you don't have to have those on. If you do have an M there, there's ways to get rid of it, but it won't affect anything. Okay. Not 3, I just used 3. Let's do 5 to the 2x plus 1 equals 30. Same situation as the last problem. We first try to express 30 as power of 5, which we can't do that because 30 is a multiple of 5, but it's not a power of 5. We'd like to set this up as a multiple of that base. That way we can test how well you all know what we're looking at here and how to deal with it. But it's not a power of 5, so we can't actually change that to 5 to a power. We have to take the log of both sides. Now, on the left-hand side, because now we have a logarithm, then the exponent, we know we can manipulate that by moving it out as a coefficient. So 2x plus 1 times log 5 is equal to log 30. We can then divide by log 5, so we have log 30 over log 5. Now, we see that we'll still have to solve for x over here, so what I recommend is going ahead and evaluating this number on the right-hand side. Log 30 divided by log 5. Comes out to be 2.11, we'll say. In fact, I actually may put the next number there for now, and then we'll approximate a little bit further later. Let's subtract our 1. So 2x is 1.113, and then if we divide by 2, now we can approximate it a little bit further. We may even choose just to leave our number in the calculator, subtract 1, and then divide by 2. This will actually give us the most accurate answer, which is 0.56 after we round. But even if we take 1.113 and divide by 2, it still rounds to 0.56, so it's okay either way. It's actually better in general if we don't round our number at any point, but it is a little bit harder to work with in that regard, so if you're not comfortable doing that, that's fine. We can approximate it and still get close enough to the answer. Yeah, that's what we end up with there. Okay. Let's see. We should definitely do this example. There we go. In this case, we have two different bases. Now they're each raised to a power. Now we can actually apply the same approach here that we just talked about in the last couple of examples. We can take the log of both sides. But now notice in each case we have an exponent on both sides, so we can take that exponent and move it out in front of the logarithm. So that is x log 5 equals 2x plus 1 log 2. Now, somehow we're going to have to get our log 5 and log 2 together. doesn't really matter on which side, but I think it'll be easier to take this log 2 and divide it over to the left. And so that's going to give us x times log 5 over log 2 equals 2x plus 1. So now we'll take log of 5 divided by log of 2. Comes out to be 2.32. Okay. So that's that number times x, so we'll say 2.32 times x. Let's now subtract 2x from both sides. So 0.32x is equal to 1. Finally, we just divide, so x is 1 divided by 0.32, which comes out to be approximately 3.13. Okay. I feel like I have my camera aimed a little bit high, but it's okay. I just need to lean back for a second. It's a little bit easier on my back that way. Alright. This early in the morning. So, if we have both sides have an exponent, even though we have different bases and bases that we cannot get equal, we still go through the same approach of taking the log of both sides, moving our exponent down as a coefficient, and then solving from there. There's a variety of ways from this point we can get to the answer, but that is the answer either way. Hopefully that addresses some of your questions that you had from the review. Now, last thing I wanted to look at today is section 8.1, which is on, no, I really hope I get it later today, just so you have a grade and you can look at it and everything. So anyway, I meant to do it yesterday. I just came down to it last night. I just didn't feel like doing it, unfortunately. This topic will be certainly easier than logs and exponents. Most of you will find this a little bit of a refreshing way to finish up the new material for the semester. This is largely old material for a lot of you, I suspect, but from previous classes. The idea with a system of linear equations is that we have two equations. Let me just show you an example. We could have, for instance, 2x plus 4y let's see that. Let's say it equals 2. Yeah, 2 is fine. And then we could have 3x minus y, and that would equal 10. Oh, Certainly. I missed that entirely. It's just the title, but it's important. But this is what we're talking about. We have two equations and two variables. And so we'll look at a couple of different methods for solving this. First method is substitution. The substitution method allows us to solve, or our intention is to solve one equation for one of the variables. And then substitute for that variable in the other equation. So, if we look at these two equations, which of those variables does it look like will be easiest to solve for? X or Y in the first or second equation? Y in the second equation, right? And the reason that would be the easiest one to solve for here is it doesn't have a coefficient. We have to be careful. We don't want to create fractions when we don't need to. And this is one such instance. If we can solve for this y, we won't have to divide by any numbers, so we won't create any fractions unnecessarily. Which is lovely. We don't want to deal with fractions if we don't have to. So 3x minus y equals 10. We can subtract the 3x. So negative y equals 10 minus 3x. And then we multiply everything by negative 1. Whoa. There we go. My camera's a little crooked again. I bumped it earlier. Anyway, now everything's crazy. So we end up with y equals negative 10 plus 3x, or we could just say 3x minus 10. That's probably more of a normal answer there. Everything seems okay on my end. Does anyone else have any trouble? I guess if you're having trouble, you won't be able to reply. Anytime we have technical issues at this point, just refresh the page and we should be alright. Yeah, my software is reporting no issues, but I never know. Are you back, Amanda? Hopefully you're back. If not, we'll be able to watch the video. Anyway, so we end up with y equals 3x minus 10. Now, we got this from this equation here, so we don't want to plug it back in here. We want to plug it back into the other equation. So we'll take 2x plus 4y equals 2, and we'll replace y with what y is equal to here, 3x minus 10. What we essentially said here is that y is equal to 3x minus 10, so we can replace y with 3x minus 10 in the other equation. From here, it's a matter of simplifying and solving. So we distribute the 4, which is 12x minus 40 equals 2. We can add these two together since they're on the same side. So that'll be a 14x minus 40 equals 2. Add the 40 over. So 14x is equal to 42. And if we divide by 14, we get x is equal to 3. Now, x equals 3 is half of our answer. Plug x equals 3 back in here, and we'll solve for y. So y equals 3 times 3 minus 10. So it's 9 minus 10. So y is equal to negative 1. And so we end up with our solution, x equals 3 and y equals negative 1. Sometimes you'll see this written as an ordered pair, x first, y second. Oops, there we go. Other times you'll see them written separately like this. So you can write it either way. If it's an open-ended question, if it's like a multiple choice, then you'll recognize immediately which scenario it is, and you just pick the right scenario. Well, that's how substitution works. You solve one equation for one variable, plug it into the other function, and then solve from there. Now, I don't use substitution method a whole lot. I find that in a very, in most problems, the second method we'll look at is a little bit more efficient and makes a little bit more sense. This is going to be the elimination method. That is exactly right, Brock. Because the two equations are linear, then the ordered pair represents the point of intersection. Exactly. Oh, sure, Amanda. I'm glad you got back in. Okay. If you need to go back and look at the video and pause it, that's fine. Elimination method. let's see. In this case, we multiply one or both equations by a number, so that when they're added together, one of the variables will cancel out. Okay, let's actually look at the same problem. 2x plus 4y equals 2, and 3x minus y is equal to 10. Now, if we want to cancel out the y's, which the y's are probably the best choice in this case, what would we have to multiply by the second equation so that this term is opposite this term? They already have opposite signs, so we're ahead of the game there. We need this to be the opposite number as well. We can multiply by 4. Exactly. Now, notice we're only multiplying the second equation by 4. The first equation does not change. Second equation, though, we get 4 times 3x, 12x. 4 times negative y, negative 4y. 4 times 10 is 40. And so when we add these together, we add each term vertically. 2x and 12x is 14x. 4y minus 4y cancels. And 2 plus 40 is 42. Now, you see that after one step, we've arrived at 14x equals 42. Remember how much work it took us to get there last time. That's one of the advantages of the elimination method, is that it does get us to this point much more quickly without all the substitution. Now, the downside is, okay, we got x, we can just divide by 14, so x is equal to 3, we know that much. But now that we have x, we still have to solve for y, and it's not quite as straightforward solving for y, but to me at least that's a minor concern comparatively as far as the efficiency this was able to allow us. So we can pick whichever equation we want, plug in x equals 3 and solve for y. Now, I'm just going to use the second equation because it looks a little bit nicer to work with that y value there, with no coefficient. So 3x minus y equals 10. We plug in x equals 3. 3 times 3 minus y equals 10. It's behind me. Okay, there we go. So 9 minus y is equal to 10, so we subtract the 9 over. So negative y equals 1, and then we divide by negative 1, and that gives us y equals negative 1. Same answers as we got before, 3 for x, negative 1 for y. Generally, I'm going to use elimination method because I feel like for me it works faster than substitution and with less of the headaches as far as, you know, if we have a problem where none of these values are just like a plain x and plain y, it's much more difficult to use substitution than elimination because you just end up with a fraction when we solve for one of the variables and then try to substitute into the other. I think elimination solves a lot of those concerns for us. So you will have your option of methods, of course. So whichever one you think will work best and works best for you, you can apply in a given situation. I'm just saying, in general, I think elimination is a little bit more efficient time-wise and prevents some of the headaches that are associated with substitution. All right, let's look at some more examples, though. Now we are on page 567, incidentally. But let's look at that one's questionable. Goodness. Let's look at 25. It's an odd problem, but I'm not actually going to assign homework from this section since we have an entire final review to look at. So this will be fine. 5x minus 6y equals 2. And nope, that's a 3. My bad. This is a 5x plus 4y is equal to 1. That's a negative 2. Nope, it's a positive 2. I'm flitting from one problem to the next. I don't even know where I'm looking anymore. Hopefully this is right. That looks right. Okay. This is a question where we look at the numbers, and we definitely don't want to do substitution here, because, again, to solve for x or y in either equation, we're going to have to divide by a 3, a 5, a negative 6, or a 4, and invariably create a fraction, at least one, if not multiple fractions in the process, and it's just going to be a big headache to deal with. That's part of why I like elimination. So we instead look at the variables, either the x's or the y's. Now, the y's already have opposite signs, so I would suggest we work with those. But we notice, there's not a whole number that we can multiply by 4 to make it equal 6. So in this case, can we think of a number that 6 and 4, a multiple that 6 and 4 have in common, that we can make these both turn into and then cancel each other out? They multiply up to 24, so we could do 24. There is a smaller number that would work, which would be 12, and that's what August is suggesting. Yeah. And yeah. Both of you are basically saying 12, although August said it in much more words. But she got down to the nitty-gritty. Yeah, we can turn these both into a 12. This would be like a negative 12y, and this would be a positive 12y. We can do that by multiplying by 2 and 3, respectively. So the point of this is that sometimes we need to multiply both equations by a number to get some kind of common multiple that we can then cancel out. So doing that, we get, let's see, 2 here, so that'd be 6x minus 12y equals 4, and then times 3, that'll be 15x plus 12y equals 3. Adding those together, we get 21x equals 7. Okay. So, it turns out x is going to be a fraction, but we can work with it. It's not the end of the world. 7 over 21, that definitely reduces. That'll be 1/3. Now here's where we have to be careful. which equation do you think will be easier to plug x equals 1/3 into? First equation or the second equation? Absolutely the top one, yes. And the reason the top one's going to be better is we're going to multiply 3 times 1/3. That's going to come out to be a whole number. It's going to be much better than 5 times 1/3, which is not a whole number. So this is where we can more efficiently pick a good problem to plug our answer into. So if we take 3x minus 6y equals 2, plug in 1/3 for x, so 1 minus 6y equals 2. Well, it looks like y is going to be a fraction also, but at least we won't have any trouble getting it. So negative 6y is equal to 1. And then we just divide by negative 6. So y will equal negative 1/6. So we did end up with fractions as answers, but if we think about it, it's not a whole lot of work with fractions in this case. On the exam, I think we strive to make them a little bit more user-friendly in the sense that we don't want you to be we don't want you to be struggling with fractions when the main thing we want to test is how well you can solve a system. That said, there is something we need to talk about regarding fractions, but we'll get to that in a moment. Let's look at another example here. This will be 28. X minus y equals 5. Negative 3x plus 3y is 2. What can we multiply by the top equation to cancel out either the x or the y? Now, that means if we have a negative 3x here, we would like a positive 3x here. So we can multiply by 3. Well, this one has an interesting side effect that's about to happen, and some of you may already see it on the horizon. What happens on the left-hand side when we add these together? Everything's gone. Yeah, both the x's and the y's cancel, effectively leaving a 0. Now, is it possible that we just proved that 0 is equal to 17 and math is just all made up things? No. 0 is not equal to 17, no matter how hard we want it to be, or any other number. It's just not equal. Okay. What happens here is we've arrived at a false statement. And arriving at a false conclusion, such as this, means that there is no solution to the original equation. Now, there is another potential scenario here, and that is, what if the numbers on the right-hand side cancel out as well, and we end up with just 0 equals 0? Well, if we got, or we had gotten, let's use proper English here, even though it's a math class, if we had gotten 0 equals 0, instead. This is a true statement, but it's a true statement that does not tell us anything about x or y. But really, what it tells us is that x and y can be whatever they want because everything's going to cancel out anyway. So in this example, if we'd end up with 0 equals 0 instead, we would say the problem has infinite solutions. So it really matters which scenario we end up with. Either 0 equals 17 or some other number that's not 0, that's a false statement. Or if we get two identical numbers, 0 equals 0 is usually what we get. Instead, then we would say it has infinite solutions based on that. Alright, I just want to work one more problem. See if I can come up with something real quick. Last example. On a new page. Sorry, I had to come up with one real quick that hopefully works the way I intend. Okay. This one does involve fractions in the original problem. I believe you have one like this on the review also, and likely one on the exam like this. The main thing to do here is, one, don't panic. That's always an important step in any math problem. Don't panic, or math test, actually, for that matter. What we want to do, because we have equations, we can get rid of the fractions here by multiplying by the common denominator. So we look at the numerator, we have 2 and 6, so they have a common denominator of 6. So we multiply everything by 6, that's our lowest common denominator. And we actually have the same number on the bottom, on the second equation, 3 and 2, the common denominator is 6 there also. Now, we don't have to multiply by the same number on both problems. It could be different numbers. It just happens that both are 6 this time. It turns out, given 1 minute to create a problem, I couldn't be more creative than this. But I'm okay with that. So, then this is the difficult part now, is multiplying by 6. What is 6 times 1/2? The important thing to remember when we multiply by a number by a fraction is that the number, the whole number, multiplies the numerator and then is divided by the denominator. So when we have 6 times 1/2, we do 6 times 1, which is 6, and then divide by 2, which is 3. So 6 times 1/2x is 3x. 6 times 1 over 6. The 6 times 1 is 6, divided by 6 is 1, so plus 1y. And then 6 times 5 is 30, divided by 6 is 5. In these two cases, we can just think of the 6 as canceling out the denominator, leaving 1y and 5. Now on the bottom, we're multiplying everything by 6, so 6 times 1 is 6, divided by 3 is 2. So 2x minus 6 times 1, 6, divided by 2 is 3y. 6 times negative 2 is negative 12, divided by 3 is negative 4. Which gets us back to the first equation I wrote down before I divided. Okay, now we can still continue with elimination. What would we need to multiply, and which equation would we need to multiply next to get rid of one of these variables? Top by 3, good. Multiply the top equation by 3. So that is 9x plus 3y equals 15. Second equation is unchanged. 2x minus 3y is negative 4. And if we add those together, the y's cancel as intended. 11x equals 11. So x is 1. We have that. Sorry. And so now we just need to take x equals 1, plug it back into one of these equations. We don't have to go back to the very original equations, because those would be very difficult to work with. We can pick one of these two, which will overall be easier to work with, and plug the x back into that. So 3x plus y equals 5. We plug in x equals 1, so that would be 3 plus y equals 5, which means y must be 2. So we get 1 for x and 2 for y. Any questions there? Okay. We didn't get to word problems, but I definitely will talk about the word problems on Wednesday when we go over review questions, because I think there's an insurance rate problem that we need to talk about there. Yeah, when we're working with monetary amounts, like US dollars specifically, we tend to have 2 points outside the decimal, which does complicate things as far as elimination goes. If we just multiply everything by 100, that does get rid of the pennies and just gives us whole numbers. That's one way we can go forward. We end up working with larger numbers, but again, the goal is to be able to work with the numbers easily and get it to a point where we can manage them. So, do you have any other questions? Yeah, so you hopefully with what we've looked at today, you can give some of the problems on the review a second look. If you didn't see how to work it before, maybe this answered your question. Otherwise, we will certainly be able to go over them on Wednesday. I don't think I'll be able to go over the whole review, but I think I have a key somewhere that I can post to that. So I don't have to reinvent the wheel. I'm really hoping I have that somewhere. Anyway, So what we'll do on Wednesday is just whatever problems y'all want me to look at, I can go over those, and if there aren't any, I'll be sure to point out questions that we just did not go over. There's one or two of them on there, yeah. And if we still have time after there's no more questions, I will pick out problems that I know will be similar to ones on the test and potentially a little bit tricky. So, but if you do have favorite problems that you would like me to work, be sure to have those ready for Monday or for Wednesday's class. So, all right, you all have a good rest of the day. Take care. Again, we're almost to the end. We just got to push through. So, matrices is actually the very next section after this one, so we're only a little bit off track there. Is that the problem that's on the exam is pretty easy, actually, but I'll talk about it. So y'all take care. I'll talk to you Wednesday. Bye.